In Unit 5, Lesson 3, we are going to cover two pretty important topics. One is using Euler's method to approximate a particular value of a function, and then our next topic will be logistics equations and using logistics growth models. So let's start with Euler's method, and let's think about what we do when we use a tangent line or a linear approximation. So when we use a tangent line to approximate a value. So I'm going to just write this up in the margins, but let's say that I know that f of 2 is 3, and let's say that I also know that f prime of 2 is negative 3. So if I were asked to write the equation for the tangent line of this curve, and I don't know anything else about this curve, but this curve f, when x equals 5, I know that I would need my point of tangency, so that's my 5, 2, and I would need my slope. That's my derivative evaluated at, in this case, x equals 2, which is my negative 3. So using point slope form, I might write like y minus y sub 1 equals m times x minus x sub 1. And so when I fill this in, I get y minus 2 equals negative 3 times x minus 5. And we don't have to do this, but I could go ahead and add that constant. So right now I have y minus 2 on the left. I could add a positive 2 to both sides of my equation. And I could think of this now as 2, I'm going to write plus negative 3. I know that's the same as minus 3 times x minus 5. So this is just another way that we could write the equation of our tangent line. So then if I'm trying to approximate a value, let's say that I want to use this tangent line to approximate f of 7. And I don't know anything about this curve f. I'll just tell you it's nonlinear. Let's assume it's a curve. So I might say f of 7 is approximately 2 plus negative 3 times 7 minus 5. So we could go ahead and do this math. Sorry, I know I'm going into the text here. So that would be like 2 plus negative 3 times 2 there. 7 minus 5 is 2. That becomes 2 minus 6. We would get our approximation would be negative 4. So if we think about what we just did, we were looking for a new y value, a new output for our function. We started with our old y value, our known y value, and then we multiplied our slope. So I'm going to say dy dx. We could just think of that as f prime of x. We multiplied that by our change in x between like our known x value, or I could even think of this as like my old x value, and my new x value. But 7 minus 5, that's just really our delta x. So when we are writing the equation of a tangent line and then using that to do what we call either a tangent line approximation or a linear approximation, we know that the further away we get from our point of tangency, the worse that approximation is. So since we made our tangent line when x equals 5, that approximation is probably good for numbers like, I don't know, like 4.9 or 5.1. The closer we are to an input of 5, the better our approximation will be. Approximating this when f of 7, so when x equals 7, we've gotten pretty far away from our initial x value. So Euler's method is a way to make a better tangent line approximation, and it's going to come back to this, the idea of just what a tangent line approximation is. So generally speaking, we could think of our new y. So like, let's say I'm trying to approximate f at some value b. That's our new y value. I'm going to think of my initial, like my known y value. So in my, in my original tangent line approximation, that was my f of 2. So that was my 5 there. And we're trying to find f of 7. That was our new y. And we're multiplying that with, we're adding to that the product of our slope and our change in x. So again, when we do like b minus a, or in like in algebra 1 where we'd say like y is approximately y1 plus m times x minus x sub 1. That's really just delta x. That's really just how far apart our new x value is from our original x value. So when we use the Euler's method, it's slightly better than a tangent line approximation because we are going to recalculate our tangent line over smaller intervals. So let's just jump into this example and we will see how it is more accurate, but we will also see how it is more tedious. So it's a little more work to get a better approximation, but sometimes we need to do this. So in this first example, we have y equals f of x, and we're told that is the particular solution to dy dx equals y minus x squared, and we know this satisfies f of 0 equals 3. So the first thing that we're asked to do in part A is to just use the tangent line at 0 to approximate f of 2. So that's not new to us. That's just a good old tangent line approximation. So anytime we do a tangent line approximation, I know that I need my point of tangency, POT, point of tangency. And so for this particular problem, our point of tangency was given to us. We're going to need f of 0, and we're told that that is 3, so that's just straight up given to us. And then we're also going to need f prime of 0. We know that that will be the slope in our tangent line. So if I'm finding f prime of 0 and y equals f, well, that's the same as finding y prime of 0. So like f prime of 0 is y prime of 0. And with just different notation, that's dy dx when x equals 0. And since dy dx is a function of both y and x, I know that's really, I'm going to have to plug in my whole ordered pair. So when x is 0 and y is 3. So we could find that really easily using our dy dx equation here. So that's just going to be y minus x squared, so 3 minus 0 squared, which is 3. All right, so we have that our point of tangency is, again, at 0, 3, and our slope is also 3, and that's all the information we need to make our tangent line. So again, using our tangent line equation, there are so many ways we could write this. We could do like y minus y1 equals m times x minus x1. I'm gonna do the version of it that looks most like this. This will make it a little easier to transfer to Euler's method. So I'm going to say that the y that I'm looking for, so in my tangent line, that's just going to be y, that's equal to my original known y value, so my y sub 1. So remember, this is x sub 1, y sub 1. So that's going to be equal to 3 plus my slope, so my dy dx, which was also 3, times my change in x, or if I'm just writing this as a tangent line equation, that's going to be x minus x sub 1. So in this case, that's like x minus 0. So we get that our actual tangent line equation is like y equals 3 plus 3x. Now, if I'm approximating f of 2, I really could have jumped to that without writing out the equation. But f of 2, so my new y value, is going to be approximately my old y value plus my slope times delta x. So since my new y value is happening at 2, or my new x value, excuse me, is at 2, and my original x value is at 0, my delta x is 2. Because again, in my original tangent line, if I plug in 2 for x, I'm going to get 2 minus 0. All right, so we get our approximation, and that is 3 plus 6, which is 9. So on this illustration, this black line segment here, this represents our tangent line approximation. So this ordered pair right here is 2, 9. And we can see that that's pretty far off. Like, we made our tangent line here where x was equal to 0, and we have moved 2 entire units on the x-axis. So we could tell that our actual value, so our actual value for f of 2 is definitely more than 9, and we won't usually have this curve, but this curve is just for illustration. So it turns out that based on this curve, that this isn't a great approximation. It looks like our actual value for f of 2 is, I don't know, like around 17 or 18. It looks pretty close to 20, not 9. So Euler's method is a way to make better approximations. So the big idea with Euler's method is we are just going to recalculate our slope over a smaller, like, subinterval of our delta x. So let's jump down to example B. This is the same curve. We're still using the same differential equation, dy dx, and we have that same initial condition of f of 0 equals 3. So we are asked to use Euler's method with starting at x equals 0. Euler's method with starting at, let's use Euler's method starting at x equals 0 with 2 steps of equal size to approximate f of 2. So the first thing I want to think about is if I'm making 2 steps of equal size, what really is my delta x? So I am going from 0 to 2. I want to subtract. I want to say my delta x is 2 minus 0. And I want to divide that by how many steps I'm doing. So I want to divide that by 2. So my original delta x up here, my original delta x over 1 step was 2. So now I'm going to divide this into 2 steps. And this might feel similar to us of what we do when we do like a Riemann sum and we're calculating delta x if I'm using equal subintervals. So 2 over 2, I get a delta x of 1 here. All right, so what we're going to keep track of is we're going to keep track of our original point. Well, we're going to keep track of all of our points. We're going to keep track of our slope, and we're going to get an approximation. And the approximation we get, we're going to use to find our next point. All right, so here's what we do. We're starting off with that initial point of 0, 3. That was the initial condition we were given. And again, to calculate our slope, we said dy dx, our differential equation, is just y minus x squared. So 3 minus 0 squared is 3. So what we're going to approximate is not f of 2, but we're going to approximate f of 1 because we're going to use a delta x of 1 here. So if I'm starting at 0, I'm going to approximate f of 1 by starting with my known, or my original, I should just say my previous x, or my previous output, my previous y value. I'm going to add to that my slope, my dy dx, times delta x. So again, that is what we do when we are making a tangent line approximation. All right, so for this particular problem, f of 1 is approximately equal. AP is not really picky about approximate versus equal sign. We said f of 0 is 3. We're adding to that our slope times our delta x, which is now just a 1. So we get an approximation of 6. So we have now approximated that when x equals 1, when x equals 1, our output, f of 1, is 6. All right, so now we're going to start with that point. We're going to start at 1, 6. And I'm going to recalculate my slope here. So I'm going to try dy dx at this point. So again, dy dx is y minus x squared. So 6 minus 1 squared is just 6 minus 1, which is 5. So now I have a totally different slope because I'm using a different point. And this point isn't on my curve. It's still a linear approximation. So now, again, my delta x is 1. So I'm going to move over 1 from my input 1 here. When I find f of 2, that's going to be my old y value. So now I'm plugging in my 6, that y value I just got, plus my new slope times delta x. So 6 plus 5, I get 11. So instead of making one linear approximation using a tangent line at one particular value, we're starting with a line that's tangent to our curve, but we're making two linear approximations on a smaller curve. And we end up getting this ordered pair 2, 11. So we can see that it's still not great. 2, 9 wasn't great. 2, 11 is a little bit better. We're getting closer to this actual point on our curve. But in the scheme of things, it's a better approximation. So the better our approximation gets, well, that means we're going to have smaller and smaller delta x's. So like the more steps that we use, the closer we're going to get to our actual value. But as you're about to see, that can be kind of tedious. So let's look at this one last example. It's the same curve, but we're going to start at 0. We're going to do 4 steps of equal size. So I'm going to encourage you to pause the video and try this one on your own, but I'm going to keep rolling. All right, so we said first to think about delta x. We know that we are going from 0 to 2. So I'm going to do 2 minus 0, and I'm going to divide that by 4 to get 4 steps of equal size. So my delta x is now 1/2. And again, I'm going to keep track of my original point and my slope and my approximation. All right, so my original point that, again, we were given is 0, 3. My original slope at 0, 3 is 3, because we found that several times now. And so, again, when I do my approximation here, I'm not finding f of 1, I'm finding f of 1/2. So I'm starting at 0, and my new input is going to be 1 delta x away from that, so 1/2. So f of 1/2, my new value, is going to be my previous y value plus my slope times delta x, which is 1/2. And so we get 3 plus 3/2, which is like what? 6/2 plus 3/2. We get 9/2 or 4.5. So now we're going to move on. So now the point that we just found is 1/2, 9/2. So we're going to recalculate our slope using that point. So dy dx is, what was it? Y minus x squared. Yeah, so dy dx is y minus x squared. So 9/2 minus 1/2 squared, which is 9/2 minus 1/4. So 18 minus 1/4, we're going to get 17/4 there for our new slope. And now we're finding f of 1, because we're starting where x is 1/2, we're moving over a delta x of 1/2. So I'm going to have my previous output, my 9/2, plus my slope, 17/4, times delta x 1/2. And as you can see, this starts to get a little icky with these fractions. We should get a common denominator there. And we're going to have to get a denominator of 8. So that should be 53/8 when we do that. All right, so now we're going to go over another delta x. So my point that we just found that we're going to use is 1, 53/8. And now when we find our new dy dx using that point, it is y, so 53/8, minus x squared, so minus 1 squared. So 53/8 minus 8/8 is hopefully 45/8. Yeah, that works. And so now we are moving over a delta x of 1/2. So we are approximating f of 3/2. 1 plus 1/2 is 3/2. So that's going to be our old output, our 53/8, plus our slope, 45/8, times our delta x 1/2. All right, so that should work out to be 151/16. Of course, I worked it out in advance. You know I can't do that kind of fraction math that quickly without writing it down. All right, so finally, we've got one more step. So we are, sorry, that was our 3/2. So we have one more step to get over. We have one more step to get over to be able to find f of 2. So again, using our previous point, we've got, our point was 3/2, 151/16. And we're going to recalculate our slope for the fourth time. So dy dx is y, 151/16, minus x squared, so 3/2 squared, which is 9/4. And that ends up being 115/16, because that's 151/16 minus what, 36/15. So now when we find f of 2, our new y value is our old y value, 151/16, plus our slope, 115/16, times our delta x, 1/2. And this should work out to 417/30 seconds. So again, if we take a look at this graph, we're not usually going to be able to see the graph, but if I look, I could see my original point of tangency was my 0,3. So that was my 0,3 right there. And when I only move over a half step, I can see my approximations a little bit better. So when we move over a half step, we got our next point was at 1/2, 9/2. Then our third point that we found, and again, these are points on this black, like these different line segments, not actually on the curve. So our third point we got, this was our 1,53/8. And then the next point we got was our, The next point we got was our 3/2, 151/16. And then finally, our final point, our final approximation was 417/30 seconds. And if we divide that, if we actually do that division in the calculator, we'll see that that number is much, much closer to the actual value of f of 2, which again, we said it's probably around like 17-ish, just based on this graph, which is drawn to scale. So as you can see, using Euler's method is really a better approximation, and the more steps we have, the better it is, but it's also quite tedious. So we're going to look at one more example on the next page, parts A and B, and I'm going to encourage you to pause the video and try these, and then just maybe play it fast afterwards to check it out. Okay, I'm going to keep rolling. All right, so our next example at the top of page 71, we're given dy dx. I want to point out too that this differential equation and the one on the previous page, these are not separable. So for our purposes in Calc BC, we don't have the option to actually find the original curve. In case you're sitting there and you're thinking like, why don't we just integrate? Why don't we just solve this this differential equation to just find out what f is? We can't do that because these are non-separable. So we really have to use tangent line or Euler's method. So in part A, we're asked to use the tangent line of f at x equals 3 to approximate f of 2. So I know I need f of 3, and that is given to us in the problem. That's 1. So my point of tangency is 3, 1. And I need f prime of 3, which is the same as our derivative dy dx evaluated when x is 3 and y is 1. So I get x minus y, 3 minus 1 equals 2. So if I were to write my tangent line as like a function of x, I would get y equals, I could do it two ways, right? I could start with y minus y sub 1, which is my 1, equals my slope, so f prime of 3, which is my 2, times x minus x sub 1, which is x minus 3. I could write it like that. We said with Euler's method, I'll often just think of adding this 1 over. So like if I add 1 to both sides, I could think of this as my old y value plus my slope times x minus 3. That's going to be my delta x. So if I'm finding f of 2, my new y value is my old y value, f of 3, plus my slope, which is 2, times, I'm plugging in 2 for x. So we end up getting that f of 2 is 1 plus 2 times negative 1. So our delta x here is negative. We started at x equals 3 and we moved to the left one spot where x equals 2. So we end up getting 1 minus 2, which is a negative 1 there. So again, f of 2 using the tangent line approximation is about negative 1. So now if we use Euler's method to do the same approximation, but this time we have 2 steps of equal size to approximate f of 2, well, I still need all the information I had before. I still need my original point of tangent C here, but my delta x now is not going to be negative 1. My delta x is going to be my new x value minus my old x value. I could almost think of that as b minus a over the number of subintervals. So we said we're using 2 steps. I'm thinking that is like subintervals from the interval of 2 to 3, or 3 to 2 rather. So divide by the number of steps. So we end up getting negative 1/2 is our delta x here. So again, my original point, I want to keep track of my original point. I want to keep track of dy dx, my slope, and I want to keep track of my approximation. All right, so we said our original point again is that point 3, 1 that we were given. When we plug that in to dy dx, again, that's just x minus y, so 3 minus 1 is 2. And so my approximation, remember, I'm not finding f of 2 yet. I'm applying delta x to my input 3. So 3 minus 1/2 is going to be 5/2. So I'm finding f of 5/2, and that's going to be my old y value. So I want my f of 3, which was my 1, plus my slope, which is 2, times my delta x, which is negative 1/2. So we end up getting 1 plus negative 1, which is 0. So our new point that we're working with is 5/2, 0. I'm going to recalculate my slope. So again, x minus y. So 5/2 minus 0 is just a slope of 5/2 here. So now to find f of 2, because I'm going back a delta x of negative 1/2, 5/2 minus 1/2 is 4/2, which is 2. I'm going to start with my last output, which was my 0, plus my slope, which was 5/2, times my delta x, which is negative 1/2. So we end up getting an approximation of negative 5/4. So therefore, using Euler's method and using 2 steps of equal size, f of 2 is approximately negative 5/4.